Let's look now at learning an HMM. So we're going to again focus on the discrete HMM, and for this lecture we're concerned with the maximum likelihood solution. So we want to find the parameters of the HMM pi, a, and b that maximizes this likelihood of the observed data sequence given those parameters. And so notice that what's not visible in this likelihood is the sequence of states. So we're integrating out or summing out the entire state sequence, which we can write this way. If we write the joint probability distribution of the observed sequence and the hidden sequence given in HMM, and then we sum over the entire sequence of states, we can get this term here. And so now we have this representation, and using the Markov property, we can factorize this as follows, where we have the conditional distribution of the observed data given the hidden state and given the emission probability matrix times the probability of this transition from state at time I minus 1 to state at time I given pi and a. And so pi is here just for the first state, in which case S0 is missing, it doesn't belong. And then a is here for the remaining transitions after the first state. And so we already know that this probability for a discrete Markov model, hidden Markov model, can be written this way. We pick out the distribution on the data for the state at time I. So Si indexes the discrete distribution vector we're going to use, and then Xi picks out the dimension of that vector. So the element in B that corresponds to the state and the observation is the probability of observing that observation given that we're in that state. Similarly, the probability of this transition is equal to the value in the I minus 1 row and the Si column, because we're saying that we transition from state at Si minus 1 to the state at Si. So this probability is encoded in this transition matrix, or if it's the first state in the sequence, it's encoded in this initial state vector. So we can plug in all three of these things in this distribution. But we don't know what the states are. We want to sum them out and maximize this marginal likelihood. However, it's very hard to do, because if we wanted to maximize this log marginal likelihood, we're maximizing the log of a sum, and we remember that that's a difficult thing to do. If we started to take derivatives, we'd find very quickly that we're in trouble, that we can't optimize these things in closed form. However, we also know or can observe that if we get to know the state sequence S, 1 through St, that this would become a much easier problem. So if we treated these latent sequences as missing data and did a joint likelihood, we would suddenly have a very easy model to learn. In addition, we can observe, I'm not going to derive it, but what we can do is we can show how we can calculate the conditional posterior of the entire state sequence, or the important parts of it, given the data and given an HMM. And this is done through the forward-backward algorithm. So therefore, we conclude that we can use the EM algorithm for this problem, and that's how it's usually done, is with the EM algorithm. And so in the following slides, I'm going to give a high-level overview of the EM algorithm for the HMM. As we recall, the EM algorithm has two steps. First, we have to define the conditional posterior distribution of the hidden data that we're introducing that we want to integrate out, given the observed data and given the model parameters we want to do the point estimate of. So we have to calculate this Q distribution on the entire state sequence, given the observed sequence and the HMM parameters. Then, given that distribution, we have to calculate the expectation of the log of the joint likelihood of the observed and unobserved sequence, given the HMM parameters, using this Q distribution. And so that's the E step, where we get this objective function, where we have integrated out the state sequence, or summed out in this case. And now it's a function of the HMM parameters, which leads to the M step, where we maximize this thing with respect to pi, A, and B. So this part now is tricky, because if we look at the log of the joint likelihood of the observed and unobserved state sequence, data sequence, given the HMM parameters, we observe that it's equal to something like this. So here I'm summing over all of the observations of the log of the probability of observing data at time point I, given that I'm in state k at time point I. And so this sum here is simply picking out the correct probability. If I want to say that I'm in state k, then this indicator will be equal to 1 for when Si equals k, which will pick out the correct probability. So this is the data level log likelihood corresponding to this term here. So we're taking the log. In this case, we're taking the log. So we now assume we have the joint likelihood. So we can get rid of this portion. And so now we have the log of this thing. And so this first term is the log of the data level likelihood. And then these two terms are the logs of the state sequence. So this term simply corresponds to the first state in the sequence. So S1, I have to sum over all of the states, an indicator of which state I'm going to say I'm in, times the log of the probability of that state to start. And then here for the remaining portion of the sequence, so for state I at time I equals 2 to the end, I now have to have an indicator of being in a particular state j at time I minus 1, and then transitioning to a state k at time I, times the log of the probability of that transition. And now this thing has to be summed over all of the state transitions in order to pick out the right one. So this is how I can represent the log of the joint likelihood here. And so the following results are taken from this classic tutorial by Rabiner called A Tutorial on Hidden Markov Models and Selected Applications in Speech Recognition. So that tutorial will have much more discussion on the forward-backward algorithm and the Viterbi algorithm as well as the results that I'm going to use from that tutorial in the following slides. So notice with the E step that we take the expectation of this thing with respect to this Q distribution. So this is the full posterior distribution of the entire state sequence given the observed data sequence and the HMM. And now I'm going to use this, I haven't defined what it is yet, to calculate the expectation here. And so now we are going to make some crucial observations. The first observation is the fundamental fact that the expectation of an indicator of an event is equal to the probability of that event according to the distribution. So if I have some distribution Q, and I have some indicator of an event X is in a set A, for example, that's simply equal to Q, the probability that X is in A, according to the distribution Q. So I have a bunch of indicators here that I'm taking the expectation of with respect to this full posterior distribution. And so notice that when I take the expectation of the event of being in state K at time I, according to this, I'm actually summing over all states at different time points except for at time point I. So this expectation of this event according to this distribution is the marginal conditional posterior of being in this state at time I, given that of being in state K at time I. So the expectation, I'll just do it for this one example, the expectation according to Q of the indicator of being in state K at time I is equal to the conditional posterior of being in state K at time I given X and given A, B, and pi, the distribution of the HMM. So remember, this is the full conditional posterior the expectation of this event of being in state k at time I is simply the marginal full of the full conditional posterior, where I've summed over all states except for the ith at time I. Okay, so that's where these new definitions are going to come in. So in the E step, let's define two things. Let's define gamma ik to be the conditional posterior probability of being in state k at time step I. So that corresponds to this. This expectation of this thing is equal to gamma ik. Also, we have expectation here. The expectation of being in state j at time I minus 1 and state k at time I. This thing we're going to call psi I j k. So this matrix, it's an S by S matrix if I have S total states, is equal to the conditional posterior probability that I'm in state j at time I minus 1. So here the first state is I minus 1. I'm in state j. And then I transition to state k at time I. So at time I minus 1, I transition from state j to state k. This matrix encodes the posterior probability. So this is a matrix S by S where the sum of the entire matrix equals 1 and all the values are non-negative. It's a posterior probability matrix. Both of these things are outputs of what is called the forward-backward algorithm. So again, we won't cover it, but the tutorial is good for covering that. So we calculate these two probabilities using the forward-backward algorithm, which we can find the details of that in this tutorial. Then we take the expectations and we get this. So notice that what I've simply done here is I have taken this very complicated writing of these expectations and replaced them with their values that we defined. So here we define the expectation of this to be gamma ik. That's what this is here. And then one more, we define this expectation of this thing to be psi I j k. That's what's going on here. So here I've taken the expectation of the log of the joint likelihood using Q, and I get something that looks like this. Now we need to just maximize this thing with respect to pi, a, and b. And so we take derivatives, we use the constraints that they have to be probability distributions that sum to 1, and we obtain this final result. And so these are the this is the M step after calculating gamma and psi in the E step. We have this M step update. So let's look at these one by one. First, let's look at the update for the probability of transitioning from state J to state K. So given I'm in state J, what's the probability I transition to state K? This is simply the expected number, fraction of transitions from state J to state K when we start in state J. So the numerator here is summing over each transition I the conditional posterior probability of making that transition at that time point. So here we're summing over the expected number of transitions from state J to state K. That's what this numerator is doing. And then in the denominator, we're summing over all of the expected transitions from state J to any other state. So here we pick a state L. We then sum the expected number of transitions from state J to state L, and then we sum over all possible values for L. And so this is simply taking this this numerator and then normalizing along the row. So here's the expected probability, the probability of transitioning to state K given I'm in state J, calculated from these probabilities from the forward-backward algorithm. B is essentially the same. The numerator is the expected number of times I observe V, the output V from state K. So here I have an indicator that the ith observed value is equal to V We have a discrete HMM here. So an indicator of observing V at time I, and then the probability of being in state K at time I. So I simply multiply these two things together, and what I'm doing here is summing the expected total number of times that I see the output V from state K. So I'm summing over all the time points. And then I divide by the total number of observations that I'm going to see from state K. That simply takes the numerator and normalizes it so the rows sum to 1. And similarly for the initial state, we can use the probability distribution of being in any particular state at time 1, and then normalize that. In this case, we don't need to, since this is already a distribution that sums to 1, to get the initial state probability. Okay, so this is the maximum likelihood solution for an HMM when we have one sequence. How do we modify this if we have many different sequences? So it's a simple modification. Simply, all we do is we calculate these probabilities for each individual sequence. We literally perform the same steps for each individual sequence separately, and then we sum over all of those sequences. So here we have a conditional posterior distribution of transitioning from state J to state K at time I in the nth sequence, and we have a conditional posterior of being in state K at time I for the nth sequence. We sum these things up over each individual sequence, and then we sum over all of the sequences, and then normalize, and we get something like this. So here in red, I'm showing that we now simply sum these values over each sequence.